Okay, so today we're going to be talking through convection again. Last time we went through boundary layer concepts. We decided that the boundary layer kind of looks like a 1D transient conduction problem. There derives from equations based on that premise. Today we're going to go through in more detail and more kind of rigor on how we actually can write equations for the boundary layer. So remember, in heat transfer, in fluid flow situations, which we have here for convection, we care really just about what's happening right between the surface and the free stream, which is by definition the boundary layer. And so we're going to go through and derive the governing equations for what's happening in the boundary layer. To do that, we go through just the classic approach for fluid flow, right? 2D fluid flow. But because it's a boundary layer, there's some special things that we can do to simplify that, the equations in the end. Ultimately, we get to a set of equations that are simpler, but still not so easily solved analytically, but give us some insight into the problem. So it's worth going through. So today is going to be a lot of control volume analysis. So you have to stick with me as we go through it. All right. So our governing equations for fluid flow, we have kind of three things that we need to worry about. We have three quantities we need to worry about. We have mass through our control volume. That has to be conserved. We have momentum in our control volume that has to be conserved. And we also have energy. And all of those three things play together in a convection problem. And all those three things become important. And so we have to do control volume analysis on each of those three components. The general steps that we're going to go through here are we'll draw the differential control volume. We'll balance one of those three quantities. We'll take the limit as dx and dy go to 0, and then we'll introduce rate equations as needed to kind of finish off the actual equations. Okay, we're going to start with mass because it's the easiest, most straightforward one. And we'll move on to continuity and momentum after that. All right, so let's starting with mass. So the idea here is, again, we're gonna try to come up with governing equations. This looks a lot like what we've done through the whole semester. Right? You have some control volume, you have to take stock of what's going in, what's leaving, write differential equations based on that. So if we start off with mass, we have this control volume, and let's say this control volume has some width dx, right? This is dx, and it has some height dy. These are differential dimensions. And we want to keep track of what's going in and out of this. So let's start on the left-hand side. So if we have some fluid that's flowing in a whatever situation, in this case, we think about a boundary layer, this little element's out in space next to the boundary layer. We can have mass flowing in from the left, right? The left, correct? So we have flowing in from the left. The mass is going to be just velocity u. Remember, that's our x direction velocity component, u times the density rho times the cross-sectional area, which is w times dy. Okay, and all of that is evaluated here at this position x on the left side. Okay, going out on the right side, then we have the same thing, right? U rho w dy at x plus dx. So this looks a lot like what we've done for conduction, where we're saying, q dot at x plus dx. We end up having to expand out that term on the right-hand side. We'll get to that in a minute. Okay, so we've done the x here. Let's also then do the y. We have in the y direction, potentially fluid flowing in. So here we have, what's the mass going across this? It's going to be our velocity v. V times rho w, what's the area w dx, evaluated at position y. Okay, and then coming out of the top, we have v rho w dx at y plus dy. Oops, y plus dy. Okay. So we have mass in and out on both of the dimensions, and then what else? Where else could we have mass going in this problem? Sorry? This is a 2D problem. So you say we aren't going to do 3D for this, so only 2D for this problem. Yes, stored. So we could have stored. So that's going to be the partial with respect to time of what's going to be stored in here would be W times the volume. Sorry, volume is W dx dy. It's our volume times the density rho. That's our stored. I'll just put stored here. We have the stored mass in the volume. Okay, so then if this is all we need to think about for this particular component for mass. So now we can actually write out our equation. It's going to be the general balance is written as in equals out plus stored. In equals out plus stored. And so now we have to go through and just kind of tally all these things up, right? So what do we have coming in? We have U rho W dy at X coming in. We also have V rho W dx at Y. So that's coming in, and then that has to equal everything that's going out plus what's stored. So let's take what's going out first in the X direction and then expand that out. So we have, let's take the X component first. So that's U rho W dy at X plus the partial with respect to X, we're expanding it out, of U rho W dy at X times dx. Right, that's the expanded out version of what's on the right-hand side there. Do you see that okay? Okay, so then that's going out. What else is going out? The same thing in the Y direction, which is V rho W dx at Y plus the partial with respect to Y of V rho W dx times dy. Okay, so that's, let's see, we've got the in and out taken care of. Now we just have to have the stored. So we'll just add that on at the end here. That's the partial with respect to time, W dx dy times rho. Right? So now we look through this and we see, just like we had in the conduction case, we can cancel out some terms. But we can cancel out what's going in here. This X with this X, we can cancel out this Y with this Y. And we can rewrite this equation as the following, which 0 is equal to the partial with respect to X of U rho W dy at X times dx plus the partial with respect to Y of V rho W dx at Y times dy plus partial with respect to time of W dx dy times rho. Okay, so now if we make some assumptions about this, well, first of all, what can we do? We have appearing here, we have dx and dy. So dx and dy are in every term. Those can get canceled out. Maybe I should do this in red pen. Dx and dy get canceled out. W gets canceled out, right? W goes away. If we have a fluid that's incompressible, meaning density is not changing, then rho also can get canceled out, right? So we would end up with what? So rho gets canceled here, and in the dx and dy terms. And then what happens to the last term here, right? What happens if rho is constant? So we have change with respect to time of a bunch of constants. So that just becomes 0. Right? So that the whole term actually goes away if it's incompressible, right? All right, so then, well, we've done all that. We go through, now we have this nice simple equation, which just says 0 is equal to the partial U with respect to X plus the partial of V with respect to Y. Right? This is conservation of mass, and this is probably something you've seen before. Actually, this whole derivation is something you probably should have seen already in fluids. It's maybe worth going again through it. Any questions on this? Okay. Cool. All right, so that's mass conservation, also called continuity. So the next thing we're going to do is now slightly more complicated, just because, not that the process is more complicated, but there's more things to worry about. So it'll get a little bit more messy as we're trying to write it out.